Hello, everyone. My name is Christina Xing. I am currently pursuing my graduate study under the guidance of Dr. Minwu Jing, specializing in medical physics within the Department of Physics. I am delighted to share our development of an attenuation correction algorithm to compensate for both cardiac and respiratory motion, which can eliminate both motion artifacts caused by heart and lung movement and attenuation artifacts. Let me first introduce a little background about the SPEC system. SPEC stands for Single Photon Emission Computer Tomography. It is a diagnostic imaging technology that enabling three-dimensional imaging of the distribution of a radiopharmaceutical within the body. Like other nuclear medicine imaging techniques, provides information about the function of tissues and organs, while modalities like X-ray, CT, and MRI primarily offer anatomical details. I would like to first go over the importance of cardiac gate SPEC for myocardial perfusion imaging. SPEC MPI is a widely used technique in clinical nuclear medicine for the detection and evaluation of coronary artery disease. In the United States, an estimated 5 to 7 million SPEC MPI studies are conducted each year, with more than 90% of this involving ECG-gated studies, commonly referred to as cardiac gate SPEC. SPEC MPI images suffer from various degrading factors, including attenuation, scatter, spectral blurring, and patient motion. For dual-gated imaging, the projections are synchronized within both respiratory and cardiac motion. In our methodology, NCAT Fenton with cardiac motion and respiratory motion were used to compare the performance of average and motion-matched attenuation correction. CMAT was used to simulate D-SPEC imaging with technetium-99M. We then added Poisson noise of 8 million photons for all phases, resulting in only 15,625 photons per respiratory and cardiac phase. To evaluate the lesion detectability performance of each method, a lesion with 20% intensity reduction at 4 locations in the left ventricular myocardium was introduced. For reconstruction, 2 methods was compared. The first method is for the reconstruction with an attenuation map average over all respiratory gate. The second method is for the reconstruction with an attenuation map respiratory motion matched with the SPEC image. Ideal reconstruction of noiseless without attenuation and scatter serves as the ground truth for the rooming square arrow calculation. On the top is a structure for 4D reconstruction with average and matched attenuation correction. Before the SPEC reconstruction, we will reconstruct each individual cardiac phases for a fixed respiratory phase. We obtained images from all cardiac and respiratory phases using 4D reconstruction of C-SPEC. Since the photon count of each individual phase is very low due to dual gating, we sum images over all K cardiac phases to elevate the photon noise. Next is the workflow of post-4D reconstruction respiratory motion compensate temporal smoothing for D-SPEC. We estimate the respiratory motion that is a deformation vector field from respiratory phases I to respiratory phase J. When I equals J, DVF is all 0. Since the DVF are more accurate from the adjacent phases, we use a weight sum to get a final temporal filtered image. To evaluate the performance of a different method, we use the rooming square arrow and the area under the receiver operating characteristic curve AZ of channelized Hotline observer for the lesion detectability. First, we would like to observe the reconstruction result for the noiseless images. Here include 4 different lesion locations. As we can see from the figure, the lesions are located in the north, south, east, and west direction of the heart wall, which look dim. When we consider utilize both cardiac motion and respiratory motion, we will get a better image quality. Also, we would like to compare using average motion and matched motion attenuation correction. To make the difference easier to observe, we draw a line profile across the heart for all cases. To measure the quantitative difference, we calculate the root mean square error and the CHO values for these 4 cases in a table. Overall, our observation indicates that combining both cardiac and respiratory motion contributes to an enhancement in image quality. As I conclude my poster presentation, I am excited to share that our next step in this research journey, moving forward, we will apply this method to real patient data and comprehensively evaluate its improvement on DSPEC diagnostic accuracy. Thank you so much for your attention.